So welcome back. Today we will take a breather from quantum algorithms and we'll be discussing real hardware problem. In particular, we will be discussing the problem of noise, which is one of the main issues in current quantum computing architectures. And we will take the chance to introduce concept of dephasing and relaxation. Now, when we work on a quantum computer, what we work with are physical qubits. And physical systems are described by Hamiltonians. The standard Hamiltonian for many of the qubit system that you might be familiar with is just given by a diagonal Hamiltonian with entry delta over 2 and minus delta over 2. What this means is that when the qubit is in the state 0, then it will have an energy of delta over 2, as one can see from this equation. While if the qubit state is in the state 1, it will have an energy of minus delta over 2, such that the qubit in state 0 and qubit in state 1 are gapped out by an energy gap delta. Now, what this means is that suppose that we apply an Hadamard gate H to the state 0, then what we create is a superposition of state 0 and state 1. And this is the state plus that we have been discussing quite a bit in the previous lectures. Now, what happens physically is that this state plus is not an eigenstate of the physical system Hamiltonian. And what this means is that this state will undergo a certain time evolution. The time evolution of the state can be very well captured just by an exponential of the diagonal matrix h of q times t over h bar. This is an exponential phase that will essentially rotate the state plus in time. This can be seen more explicitly by decomposing this matrix form into a cosine and sine function. And in particular, we observe that the state plus will remain a state plus with probability cosine of delta time over 2h bar, while it will have we will acquire a certain probability of becoming a state minus with an oscillating probability sine of delta of time over 2h bar. This can be seen quite neatly if we think about it in terms of the Bloch sphere. Essentially, we start from the eigenstate 0 and 1 of the Hamiltonian, and when we rotate it into the equator of the Bloch sphere by going to the state plus, the energy of the Hamiltonian delta will provide a way of rotating the qubits around the z-axis. The probability then of measuring a state plus in time will then oscillate, and it will be given just by the cosine of delta times sine over 2h bar to the power 2. Or in other words, it can be just be written as 1/2 plus 1/2 cosine of delta times over h bar. This is what is measured exactly in the so-called Ramsey experiment. And in particular, when we do this experiment, what we expect from theory is that we have some well-defined oscillation that go all the way from 1 to all the way to 0. However, this is not really what happens in physical systems, and this is because of noise. In fact, noise dampens this oscillation, and over time, these oscillations are not fully developed, but they will actually become suppressed. This is one example from a work in spin qubits, but essentially the same results can be found in across many of the architectures. Now, this what we are seeing here is the effect of dephasing. And dephasing can be interpreted as the decoherence or the decay of the superposition state. Why is that? This is very well explained by the fact that we are thinking about an Hamiltonian with a fixed energy gap delta. However, in physical systems, because of noise, charge noise, hyperfine noise, imperfection in magnets or imperfection in many other things, what happens is that this energy gap starts to oscillate a little bit in time. And therefore, at each realization, we will have always a slightly different energy gap between the state 0 and state 1. So what we are seeing here is the effect of dephasing. And what we do in experiment is that because we have this oscillation of delta, typically what we have is an average value of the probability, average over many realization. To describe this, we can split the energy into a mean value, capital delta, and some small fluctuation that are randomly distributed with a mean value of 0 and a certain standard deviation. By averaging this probability over a probability distribution, typically assumed to be a Gaussian, what we see is that the probability, the oscillation will start to decay with a certain amplitude that is given by a Gaussian function that decays on time. This is the dephasing time T2 star. As we can see from this plot, every time when we have different trial and we have slightly different oscillation frequencies, when we average over all the trials, then the average probability will start to decay and will give rise to a T2 star process. So now we can be more concrete here and try to see what happens at the level of the Hamiltonian. So we have defined the qubit Hamiltonian. It is just given by a diagonal of with two different entries that are shifted by a minus sign. And we describe the dephasing by a diagonal noise Hamiltonian with a certain random entry delta, which here we take as a function of time. This is, of course, not the only process that noise can cause. In fact, it's very easy to see that there is another process that is allowed, and it's transition between state 0 and 1. This is what causes relaxation. So to describe the effect of noise, we will use the Bloch-Redfield equation, which is essentially describing the time dependence of the magnetization vector. The magnetization vector is just the expectation value of the different Pauli operator along different direction, x, y, or z. Now, the Bloch-Redfield equation is comprising three different terms. The first term is describing the coherent dynamics that is given by the qubit Hamiltonian. In our case, it's just the gap delta times sigma z. We also have a term that includes stochastic processes of noise. This is described here just by a matrix gamma that multiplies the magnetization vector. And gamma essentially tells us the rate of decay of the states. The last term of the Bloch-Redfield equation is a steady-state magnetization vector that essentially tells us where the state will like to end up if the time goes to infinity. Now, the magnetization vector can actually be neatly interpreted in terms of the Bloch sphere. In particular, the expectation value of x, y, and z are just the projection onto the axis of the Bloch sphere of the evolution of the time-evolved state vector. So let us now see what happens when we only have relaxation processes. To do so, we start in the eigenstate 0, which means that the initial magnetization vector has only a component in the z direction and is equal to 1. Then we study the decay of the diagonal polarization of this state. This can be rewritten very conveniently in a simple form, where the time derivative of the diagonal polarization is just equal to minus sigma z, the expectation value of the diagonal polarization, minus the inhomogeneous term, the steady-state polarization, over a time t1. If we solve this equation, what we do find is a very simple result that says that within a time 1, even if the state starts at time equals 0, the state will decay to the steady state magnetization sigma z of infinity. This enables us to introduce another very important timescale for experiment, which is the relaxation time, t1. Now, to understand better relaxation, let us now try to connect the equation that we just found to a rate equation. And in particular, what we want to do is now try to keep track of the probability of being in state 0 over time. To do that, we first introduce a general state vector psi of time that is just a combination of 0 and 1 state with a certain amplitude alpha of time and beta of time. The magnetization vector is then just the difference between the probability of being in 0 and the probability of being in 1. The rate equation tells us that the change in probability of being in the state 0 is equal to the rate of going from state 0 to the state 1 with a minus sign, plus the rate of entering from state 1 to the state 0 with a plus sign. This is, of course, also equal to minus the derivative, to minus the time derivative of the probability of being in state 1. With this equation, we can then relate the relaxation time to these very physical quantities, the rate of transition between state 0 and state 1 and the rate between state 1 and state 0 by this very simple formula. Particularly, the relaxation time is just the sum of these rates. We can also find that the steady state magnetization is actually a combination of these rates. To summarize, we have discussed dephasing relaxation. Dephasing comes once again from the averaging, comes mostly from the averaging between different trials. And in particular, it comes from the diagonal part of the noise spectrum. On the other hand, when the qubit is coupled to the environment, other things can happen, and there can be some transition between the state 0 and 1. And this mostly causes relaxation. There is another time scale that is the T2 time scale that is related very neatly to the dephasing time and to the relaxation time by this simple formula. And this is just a combined time scale that describes how fast do the coherent superposition decay. In real devices, we always have to fight noise. To do that, there are different strategies that can be used. There are passive strategies. For example, we always try to physically reduce noise sources. This can be, for example, given by engineering better materials or engineering better devices. We can also try to better isolate the qubit from noise by, for example, try different qubit encodings that are more resilient against certain type of noise and can, for example, fight nuclear spin or charge noise or other sources of or other dominant sources of noise. We can also try to engineer a sweet spot where the qubit is insensitive to some order to noise sources. There are also active strategies to fight noise. For example, one can try to dynamically decouple the qubit state by applying a sequence of pulses such that all the error can get corrected at the end. And of course, the best strategy that we also will discuss later on in the course is to try to actively error correct all the error that are caused by noise.